let's go on. So last time we were talking about inductance. I just want to review the whole process again so that everybody's on the same page. So remember we first talked about resistance. Resistance, rho L over A, right? Length, area, resistivity. And then we had another equation with resistance where we included the effect of, at a different temperature, right? So we extracted the resistivity from a table. But if you're given resistivity at a different temperature, we had a different equation, and that equation had also a temperature constant that we used, right? So resistance is easy, no problem. Everybody's okay with resistance, right? Inductance. We went through the inductance. We didn't finish it, but we went through some of it. And then we said that it really starts from VL is equal to L di by dt, and we said that, bring dt on one side, so VL dt is equal to L di. If you integrate, we said that you will end up, bring this here. So integrate, you end up with current on one side, and this integral of voltage, we said, is where Faraday's law. This is the same as Faraday's law. Bring dt on one side, so this integral of voltage is equal to the flux multiplied by the number of turns, which is the flux linkage, right? So this integral here is the flux linkage. So L is equal to lambda over I, right? So our objective to calculate inductance is to do what? To find out, this is inductance of a conductor carrying current I, right? Our objective then is to calculate this flux linkage, because we know the current I that it's carrying, right? But our objective is to calculate flux linkage. And similarly with capacitance. Capacitance, Vc is equal to, so we need to calculate flux linkage, right? That's our objective. And we need to calculate flux linkage, all the flux linkage linking this specific conductor, right? So if you have a conductor here, it will have flux around it. Let's say this current is coming in, so magnetic field is in this direction, right? This magnetic field intensity, H, right, has a corresponding density, right? And we know the relationship between B and H is mu, and we assume that it's constant, so we assume that it's the relation between B and H is a constant mu only, and we assume that this is an error, so we dropped mu r, and we said this is just mu naught, for example, right? So we from H, there's a corresponding B, and then B is equal to what? This is flux density, number of flux lines per unit area, right? So if I look at all the area around the conductor, right, I integrate all the area, means I'm summing. If I want to sum up all the area around the conductor to look at my total flux, then it's an integration process, and the result of that was what? B is equal to phi over A, right? So B times A, right? B times the area. B times the area was equal to flux, total flux, right? And this area was equal to what? This area we said was the area that the flux lines cross, right? And we said that this conductor is a 1 meter length, and the area that it will cross is sort of, this is the differential area here that all the flux lines will cross, right? And we did the integration, from, this is sort of extending with the radius, right? So all the flux lines are actually, so if I look at this thing here, zoomed in, this area, the flux lines are cutting it this way, right? Right, the flux lines are around the conductor, right? They're around the conductor, so they are cutting. So this is my conductor here, right? And this is on the radius. This is the radius that I'm looking at all the flux from the center of, or the core of the conductor, all the way to some point out in space, right? So this is on the radius, and I call this, up to here was r, up to the radius was r, and then up to any point x in space, it was, some distance x from the core of the conductor. and then this length here was dx, and sorry, the width here was dx, and the length of the conductor that I said was 1 meter, right? So we sort of multiplied after that. We took the B, that the flux density that we got, and we multiplied that by basically dx multiplied by 1, right? So we integrated B with distance, right? That gives us what? That gives us the flux. This flux is linking the conductor, right? Outside the conductor, these flux lines are encircling the conductor, the full conductor. Inside the conductor, so it's linking one turn, right? So outside the conductor, this flux that we've calculated is linking the one conductor that I have. So if I go to Faraday's law, what is n? What is the number of turns that I'm linking with this flux? 1 if I'm outside the conductor. How about if I'm inside the conductor? If I'm inside the conductor, because magnetic field exists inside the conductor. Electric field does not exist inside the conductor, right? Because if you have an electric field, that means there's a voltage difference. If you have a voltage difference, that means there's current flowing, right? So, I mean, if you have an electrical conductor, there is theoretically no voltage difference between 2 points inside the conductor, right? If you have a conductor with resistance of 0, for example, right? Then inside the conductor, there cannot be voltage difference between points if the resistance is 0, if you're ignoring the resistance of the conductor, right? So that's why for electric field, we only look at outside. For magnetic field, we look at the contribution of the magnetic field inside the conductor and outside the conductor, right? Outside the conductor, and again, our objective is to calculate flux linkage. So, but this flux linkage now is contributed by internal flux linkage, or flux that is linking a part of the conductor, right, up to from the core of the conductor up to a point x away, not the full radius, right? When you're looking at flux linking outside the conductor, this n is equal to 1. And as soon as we've calculated phi from here, h, then b, then phi, then you're done, right? Then you stop, because you calculated your flux linkage. Because in that case, the flux that you've calculated is equal to the flux linkage, right? But in the case where you're looking at internal and external, you're looking at internally, it's only linking a portion of the conductor. This portion of the conductor is how much? Is defined by the ratio of the big area to the small area. The ratio of the full conductor, the ratio of the portion that you're linking. So you're not linking 1, d lambda is not equal to d phi anymore. It's, d lambda is equal to what? A portion of d phi. So k times d phi. This k, this constant, is equal to what? Is less than 1, because obviously when you're linking the full conductor, it's 1. So this portion is less than 1. It depends on the ratio of this area here that you are currently integrating up to and the full area of the conductor. So we said it's x over r squared, right? Because area is 2 pi x squared, right? So it's the pi goes with the pi, so we end up with x over r squared. So we calculated lambda internal plus lambda external, right? And then after you have lambda, you finish. You divide it by the current in that specific conductor, and you will get the inductance, right? This is due to one conductor in space, right? This is due to a single conductor in space. You have one single conductor in space that has flux lines inside and outside linking this one conductor, right? All these flux lines are linking the conductor inside and outside, and you've calculated lambda internal and external. How about if I bring another conductor? This conductor also has flux lines and with current flowing through it, right? Assuming current is in this direction here, and then current is in this direction there. So here, magnetic field would be opposite, for example, or it can be the same direction. Does not really matter, right? But the idea is these are flux lines. These are flux lines here that are also linking this conductor. But as this radius, or as this, as this distance gets larger, right? These the magnetic field. If the current is, if you have current flowing through the conductor, the magnetic field is basically circles around the conductors, right? So these circles, you can look at it. You can look at the magnetic field strength, very close, or you can look at the magnetic field strength very far away, right? So if you look at the effect of this conductor very far away, then what will this conductor be doing? This conductor will also be, the flux lines from this conductor will also be linking this one. How about this one? Same. So what we want to do is, but if each of these are alone, then we know how to treat them, right? But if they're all together in one space, what do we need to do? We need to look at what? Eventually what I would like to do is calculate the inductance of this phase. This is phase A. I want to calculate the inductance of phase A. So inductance of phase A is equal to what? The total flux linkage, it's total flux linkage, right? When it was alone, it was flux linkage due to that conductor, right? But this is not, it's not alone anymore, right? It's in a space with many other conductors, right? So I would like to calculate the total flux linkage of that conductor. And then divided by, so this is total flux linkage of conductor A, and divided by the current flowing through it, then I calculate inductance of phase A. So this total flux linkage will include contributions from conductor A, which we know how to do. We calculated lambda for that specific conductor, right? And we calculated lambda for the specific conductor from its center or its origin all the way to some point P in space, right? That's what we did last time. Some point P in space. I can do the same. I can, this lambda now is, this lambda A is a contribution from the flux lines due to this one. How about the flux lines due to this one? They also need to be considered. We know how to calculate the flux linkage due to this conductor. This flux linkage due to this conductor between point, what? Now I would like to see the effect of this conductor and this conductor. Remember what we were doing was, we ended up with an equation. Let me write the equation. I'll show you the equation on the slides. There. This equation here, lambda 1, 2. So the flux linkage between points 1 and 2 in space around the conductor is equal to 2 times 10 to the minus 7 I natural log d2 over d1. d2 over d1, right? This was, again, this was this is the external. Remember, the internal flux linkage was half times 10 to the minus 7 I. External was 2 times 10 to the minus 7 I natural log d2 over d1. So then we calculated the total flux linkage due to that conductor carrying current, which was this expression, right? This expression, after that, what did we do? We sort of simplified. We used some identities from the logarithms, right? And we also, called this e to the minus 1/4 r to call it r prime, just for simplification. And we sort of calculated the flux linking a conductor, this single conductor, up to a point P in space. So from its core up to a point P in space was equal to 2 times 10 to the minus 7 I natural log d over r. Is everybody okay with this? I mean, do you see where we're getting this from? Right, let's go back. Just quick. Right, we start with Ampere's law. Integral of h dot L is equal to I enclosed, right? This L is equal to what? 2 pi x, this path here. And the h of interest is the magnetic field intensity at that's tangential to this path. That's h of x. And the current enclosed internally is Ix. It's a portion of the large current. So we calculated h. And then from h, again, it's a portion of the current, so we can substitute with, remove Ix and write Ix in terms of I. Ix in terms of I is the ratio of the areas as well, because we said that the current density is constant in this conductor, meaning the current, all the current that's flowing in this area versus the current flowing in the large conductor, the ratio between them is the area, because the current density, the current per meter squared or per centimeter squared is fixed. So the relation between Ix and I is the area of the small area, which is this circle and 1 meter in length. So the cylinder, this cylinder and the large cylinder. So we calculated H. After H, we calculated B. The relationship between them was only mu naught. We ignored mu r because we said that this is a non-magnetic material, so it's like air. And then after that, we wanted to calculate the total flux linking the conductor. So for us to calculate total flux linking the conductor, given the flux density, so I have flux per unit area. What do I need to do to calculate the total flux? Integrate over the areas. So integrate the flux density over the full area. So take the flux density. The area was the dx, this dx section, and 1 meter in length, right? So this is dx by 1 meter. It just happens to be, because dx is this extension of this, so this is x here. If I increase this circle radius a little bit, it's dx, right? This is where the flux lines are cutting, perpendicular to this area. This has a width here, dx, length 1 meter. So d phi is equal to b times dx. So this is the flux density. This is the differential area that it's intersecting. This is the differential flux. For me to calculate the total flux, I integrate the flux, differential flux, over the differential area multiplied by the flux density. I can calculate that, but my objective is to calculate the flux linking the portion of the conductor internal to inside, a portion of the conductor, not the full conductor. So I have to find the relationship between flux and flux linkage. The relationship between flux and flux linkage for this area of the cylinder or area of the conductor is the ratio of the two areas as well, right? So this is the relationship between the flux and flux linkage. So then I can calculate flux linkage internal to the conductor from the core of the conductor, 0, to the radius of the conductor. So this is all the flux inside the conductor due to the current the conductor is carrying. So from 0 to R, right? Everybody's okay with this? And that is this half times 10 to the minus 7 times I. If I want to calculate the corresponding inductance, you take the flux linkage divided by the current that the conductor is carrying. So divided by I, you get this inductance, right? That's flux linkage internally. We said that we still have to account for the external flux linkage up to a point P in space, right? Because there's flux lines inside the conductor and then outside the conductor to infinity, theoretically speaking, right? So first, I need to calculate the external flux linkage. The process is very similar. Integral of h dot dx is I enclosed. I enclosed now is I. And h of x of interest is the magnetic field strength of interest. And the 2 pi x is now, x is greater than r. Right? So we automatically know here that since we're outside the conductor, we're linking the one conductor term. So d phi and d lambda are the same. So I do the same process that I did before. From h, I find b by multiplying by mu naught. I find the relationship between d phi, which I can calculate from the flux density, and then I find the relation between that and d lambda. Since I am now linking the full conductor, n is 1. There's no difference between the flux that I'm going to calculate or they're going to integrate over the full area and the flux linking the conductor. They're the same. And then I can do the integration between what? Between any 2 points in space, really. d1 and d2. If I have any 2 points in space, I can calculate the integral of d lambda, which is lambda 1 and 2, lambda 1, 2 is the flux linking any 2 points in space, 1 and 2, that are distances d1 and d2 away from the core of the conductor. And then if I would like to look at the specific flux linkage from, because before I calculated the flux linkage from the core to the radius of the conductor. Now I will calculate the flux linkage from the radius all the way to some point P in space. Right? And now I will have total flux linking that conductor. Right? From its core all the way to a point P in space. So I will take this D1 and make it equal to R, and D2 make it equal to some point P in space. That's D, distance D far away. Right? So this integral, before I substitute with R and P, this integral will be 2 times 10 to the minus 7 I natural log D2 over D1. If I want to calculate the corresponding inductance, I just divide by the current that the conductor is carrying, which is I. I don't care to do that now. I will do that next. So now I have an inductance due to magnetic field outside, an inductance due to magnetic field inside. There are two inductors in series, inductances in series. I can just add them. Or I can add the two flux linkages and then divide by the current of the conductor. So is the process clear? Yes.
So when you talked about the total flux linkage, there are more than one.
Now it's still one conductor.
Yeah, so we didn't.
No, we didn't do that yet. I'm still doing one conductor. I want to make sure that you understand the one conductor case. So the one conductor now, I will add the two flux linkages that we calculated before, and then do some simplifications. After do some simplifications based on logarithmic properties, etc., etc. You end up with the flux linking a conductor carrying current I up to a point P in space is 2 times 10 to the minus 7 natural log D over R prime. So everybody's okay with this? Right? So this is flux linking conductor P, flux linking conductor carrying current I up to a point P in space. And of course, we talked about the inductance being the sum. I'll take this is the total flux linkage, divided by I, which is the current of the specific conductor I want to calculate the inductance for, and the inductance is 2 times 10 to the minus 7 natural log D over R, Henry per meter. This is the inductance of the transmission line, Henry per meter, if it's a single conductor. Now is the case where I have multiple conductors. To go to multiple conductors, what's going to be the difference here? I have to still work with this equation, but instead of now, okay, so this is, let me draw. Right, this equation is what? This is the one conductor here, and I have the flux linking it all the way from from its core, right, all the way to some point P in space. If now I have another conductor here, what is the flux linking this conductor from its core to some point X in space? Assuming these don't see each other, assuming they're too far apart. It's the same as this, right? It's the same. It's 2 times 10 to the minus 7 I, assuming this I is the same I, then natural log D is the distance between the core and this point P in space, and R prime is the effective radius of the conductor, which is 0.7788 times the radius, right? How about if they see each other? If the conductors are affecting each other. If the conductors are affecting each other, remember this equation was originally what? This equation was originally not P, it was originally what? 1, 2, right? Lambda 1, 2, and I took 1, D1, and made it, originally I had distance, this is distance D1, and this was distance D2 away, right? And this was 0.1 and 0.2, and the equation was lambda 1, 2 is equal to 2 times 10 to the minus 7 I natural log D2 over D1, right? This was my original equation, and then I took D1 and I brought it to here. I said D1 is equal to R, and D2 is equal to D, which is the distance between the core and point P in space. And that's how I ended up with this equation, right? But I can go back to the general equation. which is 2 times 10 to the minus 7 I natural log d2 over d1. If I go back to the original equation, what does this tell me? With this equation, I can find the effect of this conductor on this conductor. How is that? I can make d1, for example, here, the distance between these two conductors. And I can make d2 this distance, the distance between this conductor and the same point in space p. What does that buy me? That tells me the effect of this conductor on the flux. Flux patterns add vectorial, right? So if I have, flux, all the flux between these 2 points, or all the flux between these 2 points, which is linking this conductor due to itself. But then I also have all the flux between the same 2 points, right? So, and I add them to this existing flux that was due to this conductor alone. So I take now this new flux that is due, new flux linkage that is due to this new conductor coming into the equation, but between the same 2 points, between this conductor's surface and some point P in space, right? And then another conductor, and its effect also on all flux linkage between this conductor's surface and some point P in space, right? And what did I do? Then I found the effect of all of these conductors on the flux linking this one original conductor, right? So that is the total flux linking that specific conductor. And then after that, if I want to find its inductance, assuming this is phase A, for example, then I have, this is lambda total divided by IA, by the current that is carried by this conductor, right? So this is what this now, instead of making d1 equal to r and d2 is equal to d, I will make d1 equal to the distance between, let's say, I'll call this conductor K, and I'll call this conductor I, right? So I'll make this d1 equal to dki, right? I'll make this d2 equal to, dip, right? So then I can use the same equation, but I just instead, figure out the smart way to substitute with d1 and d2, right? So and then I add it. So how about this conductor? I have my d1 is this distance between conductor. This is conductor M, for example, on conductor M and conductor K. So d1 will be dmk, and then d2 will be dmp in this case, right? So it's the same equation. I just will play with this d1 and d2. Is it clear what we're going to do? So then I will, so that's what we have in the next slide. So here, the other quality that's interesting, and this will be interesting when we look at three-phase. The sum of all the current, in a three-phase transmission system, transmission tower. This tower, at the end of the day, our objective is to we have a tower, and this tower has another tower next to it, and we want to calculate this is my three-phase lines, right? These are my three-phase lines. I want to calculate the parameters of my equivalent circuit between, this tower and this tower, for example, or between a couple of towers and each other, right? So I need to basically consider what are the conductors that are in the same vicinity. They will be phase A, phase B, and phase C. In a balanced three-phase system, what does IA plus IB plus IC equal? 0, right? So, and typically a tower would either carry, so this is something we will use to simplify, because remember we're going to add the flux linkages now, right? And the flux linkages, they will contain currents, right? The equation for flux linkage contains current, right? So now we will have flux linkages due to flux linkage conductor A, which will have components of, or the effect of current flowing in IA, effect of current flowing in IB, effect of current flowing in IC as well, right? They will all be there. But we will need to simplify this total summation that we come up with. We will need to simplify it. One way to simplify it is knowledge of the physics that we have happening. Balanced three-phase systems, sum of the three currents is 0. So we will use this identity to simplify the big summation we come up with. And a tower will either carry a three-phase, and this is typically called a single circuit, or sometimes a tower would carry a double circuit. So one tower would carry, for example, two three-phase systems. And this is called a double circuit. So this is phase A, phase B, phase C, another phase A, phase B, and phase C. Two completely different circuits, right? Some towers will carry two different circuits. Okay? The benefit of double circuit towers is what? I need less tower space to carry two circuits. And I can also this gives me redundancy, right? If one of the circuits fails, I have redundancy. I can use the other circuit to feed the loads, for example, if it's going to the similar location, for example, right? So it gives me redundancy. It's threats that we see or hear about these days. Even though it's crazy stuff, but still it happens in the world. So power engineers have to deal with it, right? So you have to make sure that you build a redundant system, for example, right? So double circuits are nice, and you don't have, and the tower footing, tower footing or tower space is 1. I don't have to have space for 2 towers, which is more painful, right? I have to occupy more land cost, visual impact, all of this other stuff that we talk, roads that lead to these towers, all of that is reduced if I use a tower with double circuits. But in a double circuit tower, again, what is the sum of current? Okay, you agree that this conductor's current will affect the flux linkage around all the other conductors or not? They all affect each other, right? These are all in the same vicinity, right? So the flux lines or the flux lines due to currents from this conductor will affect this conductor, this conductor, this conductor, this conductor, and this conductor. One conductor will affect all the others. But in a double circuit as well, what is the sum of currents? What is the sum of currents in this plane? This is one three-phase circuit. This is another three-phase circuit. So IA plus IB plus IC plus IA prime plus IB prime plus IC prime is equal to what? Also 0, right? So this identity will always hold, right? The sum of the currents in a plane will always hold, because we're either going to carry a double circuit or a single circuit. Regardless, this identity will always hold here. So this is something we will use to simplify. And then we said we will have 2 general equations. Actually it's one equation, but we change the terms accordingly, right? We will have one equation where the terms are the distance between the conductor and the point in space, so conductor, and some point in space, so conductor K, and some point in space P, right? That's the flux linkage due to this specific conductor carrying current I up to a point P in space. And then the other equation is the flux linkage due to a conductor carrying current IM. This is conductor carrying current IM between what? Between these 2 points in space, right? Because I want to make sure that I'm looking at the flux linkage between the 2 same points that are affecting my original conductor, right? So it's between the distance here is, this is conductor K and this is conductor M. So it's D PM, this is point P and conductor M. So it's dPm over dKm, right? So, and this will apply, this M I can change now to 1, 2, 3, 4, blah, 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 right? All the other conductors in the vicinity, right? So I can do that. So I basically have two equations that I will add up, but this will be inside a summation. And the summation will be based, on the variable m, where m stands for all the conductors in space. If m happens to be equal to k, then I'm using this equation, right? If m happens to be equal to k, it means that I'm looking at the effect of one conductor on itself, right? If m does not equal to k, then we use this equation. Easy? So really, this is a summary of inductance calculation. And after that, you take, and for the specific phase you want to calculate the current for, add the flux linkages, divide by that specific phase's current, and that's it, you're done. Okay, so there are no questions there. So this is the summation. So they took this, they took the first term, this one, and the second term, and they put them inside this summation, and they did some simplifications. I don't care to do the proof of that is in the textbook, okay? And then what they do after that is actually something interesting. So the proof, okay, from here, from the addition of this and many of those is basically this equation, equation 24. The proof, the details of the proof of that is in your textbook. I don't care to know that. It's something you can go through the derivation. But the next point I want to show discuss is the following. They will simplify this even further. The one way to simplify this further is, okay, now I'm looking at, after they've, so they've added these two together, and they added this and many of those, and they did some renumbering and used this identity, and they wrote lambda kp. Lambda kp is what? Is the flux linking conductor K up to a point P in space, due to itself and everything around it. Right? That's what this is. Right? This point P in space, if this point P in space is very, very far away, right? I mean, this point P in space can be far away. I can look at the effect of, calculate inductance due to all the flux in the world on this conductor, right? So if I do that, what is dPm over dPm? Where m is one conductor, small m is one conductor, capital M is another conductor. dPm is what? The distance between infinity and one conductor. And then this is distance between infinity and another conductor. So what are these equal to? What's this ratio equal to? What's this ratio equal to as a number? This is a very large number, and this is a very large number. So the ratio is equal to 1. Natural log of 1 is 0. So this term will cancel out, right? And you will end up with lambda kp equal to only the first term. Here, this is where they talk about that. You will end up with only this term. So this is the total flux linking conductor K up to infinity. So that's why they dropped the P term, because this is a total flux linking conductor K due to itself and everything around it. When K is equal to M, then this is going to be the radius. When it's not, then it's the distance between the specific conductor and the conductor of interest, right? So any questions on this? We will apply it now in an example, right? This is summation, right? This will be conductor 1, conductor 2, conductor 3. The M's are conductor 1, 2, 3, 4, 5. If M happens to be the same as this one, then this dkk is going to be equal to the radius of the specific conductor, right? It's the distance between one conductor and itself, right? So it's the radius of that specific conductor, right? So everybody's okay with this? So now let's look at applying this as an example. I think it will be much easier if we do that. Again, this is really the only equation that you need for calculation of inductance. Period. Everything else was okay, derivation, proof, and it's good to understand. Starts from field strength, flux density, flux. I want flux linkage, so I understand there's the relationship between flux linkage and flux. If I'm outside the conductor, then I'm linking the full conductor. They're the same. If I'm inside the conductor, then the relationship between them depends on the area that I'm linking versus the full area of the conductor. That's really the physics behind all of this stuff. And then you ended up with this flux linkage equation, right? So this flux linkage equation, we'll apply it now on a single phase system. So you have an example. This is one example. We have current flowing in one conductor in this direction, current flowing in another conductor, the opposite direction or the same direction but with a negative sign, right? So this is a single phase circuit. Single phase circuit has current going and then coming back in the other wire. So I would like to calculate the inductance of the single phase circuit. So how do you calculate the inductance of the single phase circuit? Go back to this equation. I have two conductors now. So let's calculate the flux linking phase A. Flux linking phase A is equal to 2 times 10 to the minus 7 IA, right? Natural log 1 over the distance between conductor A and itself, right? So 1 over r prime in this case, right? When dkk, when k is equal to m, then this is dkk, and it's equal to 0.7788r. You substitute the radius in this case. So that's the first term. How about the second term? So plus the summation, second term of the summation, plus I have two conductors, right? In this area. So plus IB in this case is equal to negative I, right? Because our current was going in one direction, going back in another direction. So it's plus IB, or in this case, it's the same current magnitude, but with the opposite sign, natural log 1 over the distance between the two conductors. So this is the total flux linking phase A. The inductance of phase A now is this total flux linkage divided by the current in phase A. Right? So that's what they will have here. So lambda x, which is phase A, for example, 2 times 10 to the minus 7, and the summation. The summation has Ix natural log 1 over d xx. If these two subscripts are the same, that means I'm looking at the effect of the conductor on itself. This is the distance between the conductor and itself, so just the radius. And then this is the distance between the two conductors. Ix and Iy happen to be related by the fact that they are the same magnitude but opposite signs. So the summation becomes 2 times 10 to the minus 7, I natural log d over r prime. Okay? Inductance, you take this, divided by inductance of line x is flux linking conductor x divided by the current the conductor is carrying, which is Ix. So it's lambda x over I. It's this. How about Ly? Same. It's Ly over minus I. Right? And then this single phase circuit is it's going, feeding my load, and then coming back. This is Lx, Ly. So what is the inductance of the transmission system? Forget about the load. Inductance of the transmission system is Lx plus Ly. Your transmission, remember, you're trying to find your transmission line inductance. Right? That's the whole objective, trying to find the transmission line inductance between 2 points. So this is a single phase transmission system. So this single phase transmission, you want to draw your single phase equivalent circuit, right? That's what you want to draw. What do you include in your single phase equivalent circuit? Your sending path inductance, and then your return path inductance, and then you can draw your load. So this is your single phase equivalent circuit for this system. So you have to consider the sending path inductance and return path inductance. So, and then here. So Lx is equal to this, and Ly is equal to what? You can redo this, and it will be the same, but with a minus sign of the inductance for the current, yeah, right? So lambda y is the same, but with a negative sign, right? So then you find corresponding Ly. Ly is equal to lambda y divided by the current. Of course, there's no such thing as a negative inductance. It's an inductance, yeah. So it's 2 times 10 to the minus 7 natural log d over r prime y. If the two conductors have the same radius, then this rx and ry are the same, right? And I end up with L is equal to Lx plus Ly, which is equal to the two summations, the two results that we calculated. Simplified. If Rx is equal to Ry, so sorry, this is Rx prime is equal to Ry prime, not Rx prime is equal to Rx prime. Okay, so this is Rx prime equal to Ry prime equal to R. Then I can simplify this even further, and these will be R squared, go out of the square root as R prime here, right? So this is now the inductance of my single phase transmission system, right? So another advantage of single phase system, another disadvantage of single phase systems that we will see now, that the three phase system has less inductance. So this is, I have to live with this inductance if I want to send power and receive power on single phase. This is 4 times 10 to the minus 7 natural log blah blah blah, right? We will find that the inductance, the per phase inductance of a three phase system is going to be half the inductance of a single phase system. We will do the example now. So this is another example of three-phase versus single-phase transmission. Besides what we talked about originally, where we are reducing the copper needed to transmit a certain amount of power, the inductance of transmission, of transmitting power in a three-phase system is half of the single-phase system. So, which means that I require less reactive power supplied by the generator to feed a load if I'm supplying the load in three-phase. Right? This is another big advantage of three-phase systems because, again, generators, if you're consuming the reactive power of the generator to supply your inductances, right? These inductances are consuming reactive power, right? Then your generator's capacity is affected, right? Because generator capacity is in apparent power. If you need to supply reactive power, it eats away from your ability to provide real power, right? So this was one example. Here's another example on a three-phase system. So we have three-phase conductors. Here I have a configuration where the distance between the conductors is all D. So I have a three-phase system. Is this what you see on a tower or no? Are the wires typically hanging like this? Nice triangle, blah, blah. They're not, right? So, but we'll see why we end up with, why we use whatever is happening versus what's the relationship between that and this example, right? This example I have what? I have three conductors, A, B, and C, each with radius R, so they're the same conductor. And the phase spacing between phase A, B, and C is distance D, right? So that's the example that we have. So again, go back to the equation. Equation now will have three terms in the summation, right? We also have the identity that IA plus IB plus IC equal to 0, right? Then we go back to, and I want to calculate the inductance of each phase because the objective is always to calculate my single phase equivalent circuit. So I want to calculate the inductance of each phase, right? So how do I do that? I look at the effect of the conductor on itself, which is phase A on itself, and I end up with an R here. And then phase B on phase A, phase C on phase A, right? And that's these other terms here, and then that's why, and I use the same D in the denominator, right? So that is the total, this is now the total flux linking phase A, due to itself and the two other conductors in space associated with it, B and C. And that is equal to, okay, so that is, these are, you can take the natural log 1 over D, natural log 1 over D as a common factor, and you end up with IB plus IC here. And IB plus IC from our identity is equal to minus IA, right? So I rewrote this in terms of IA only as 2 times 10 to the minus 7 IA natural log D over R prime. Right? So this is the total flux linking conductor A due to itself and phases B and C. If I want to find the inductance, I divide it by the current in phase A. And this is going to be the inductance. This is 2 times 10 to the minus 7 natural log D over R. How does this compare to the one before? Before, for the single phase, it was 4 times 10 to the minus 7 natural log D over R. Or D over X, D over Rx. Right? So, in a three-phase system, I can draw the single-phase equivalent circuit. So now this is my single-phase equivalent circuit for my three-phase system. Now I have an LA, my source, and my load. This LA is half what I had before for the single-phase system. So this is a big advantage of three-phase system. Right? Huge advantage of three-phase system. We're okay with this? Now, how about what if I, in reality we don't find this happening, right? In reality we find the conductors, hanging on transmission lines which way? We find them, either this way, this would be the tower, for example, carrying the conductors this way, or they would be on a double circuit tower, for example, carried, for example, this way, right? So this is D1, this is another D, 2, and this is another D3, right? This and this distance may be the same, but this is not the same, right? So if that's the case, then my equation here will not look like this. I cannot simplify it this way, because I cannot use the same D anymore and simplify, and things become very nice, right? So what will I end up with? I will end up with, here what is LB and LC for this configuration where D is the same. LB will equal to LA will be equal to LC. They will all be the same because D's are the same. If the distances are the same, then I can simplify and they will all look the same. LA will equal LB equal to LC, and they will all be the same. How about if two of the conductors, the distances between them are the same? Like if I have them on, they're next to each other. If all the conductors are next to each other, this and this conductor have a distance D between them. But how about these two? They have a distance D prime between them, right? So am I going to be able to get this same inductance anymore? I will not, right? So how do we deal with that? I mean, how do we deal with that? Yeah. If we do that, we will get different inductances. You tell me, is that bad? What was the assumption that I was always saying about balanced three-phase systems? Yeah? That I can draw the single-phase equivalent circuit. If my LA is different than LB, different than LC, can I draw a single-phase equivalent circuit? It's not balanced anymore, right? So what's the solution? There is a solution. The good thing is that there's a solution, which is why we did everything we did before. Otherwise, we would have been wasting time before, right? But how do engineers deal with it? Yeah. Think of what you see on the transmission line. Are the transmission line cables always just this parallel to this, parallel to this, or sometimes you see them intersecting, going on top of each other, and you wonder why they're doing this? No, you never pay attention. It's like you never fancy like, wow. No, if you drive by a transmission, a transmission line for several kilometers, for example, you will see that they will swap places. They will switch places, and it's called transposing. Transposing. It's called line transposition. This line transposition is to deal with this. So the lines are transposed so that the equivalent inductance, as seen for the full line, is the same. So these distances are swapped so that always you have they call it the geometric mean distance. The geometric mean distance, the last slide we will define geometric mean distances, and the geometric mean distance will be it will be a number that will always give us the same D that we will use in the equation, but this, instead of D, actual physical distance, it will be a mean distance. It's called the geometric mean distance. It will be based on the distances between the actual conductors in themselves, but it will give you the same number that you can use in this equation. You will use the same number in this equation, but it will be not the actual distance between them. It will be a square root of the multiplication of the three distances, a cube root of the multiplication of the three distances at a certain plane. Right? And it's called geometric mean distance, and you will just use that in the equation. And if you use the same number, that's it. And then all the inductances are the same. And what I said before for the past weeks was not science fiction. We actually have balanced three-phase systems, and life goes on, right? So isn't this cool, the fact that you're transposing? As an engineer, So this is what they were talking about here. So if the three conductors are in horizontal configuration, the inductances are not equal, and we need to use transposition in longer transmission lines. That's what happens. And the last slide talks about transposing because it applies for capacitors and capacitance and inductance as well. So that's why I will only in the last slide we'll look at capacitance now quickly, and then we'll see what we can do. So capacitance. So inductance, we started with magnetic field intensity, flux density, flux. Looked at this relation between flux linkage, and we took flux linkage divided by current to find inductance. Right? Capacitance. How do you do capacitance? Again, how did we come up with the understanding of the inductance from a basic equation? VL is equal to L di by dt, right? So, and then we brought dt here, integrated. We said this is flux linkage. Took that, divided by the current. We said this and that. So we have to do the same for capacitance. right? So IC equals C dVc by dt. This is the first order differential that links voltage and current across a capacitor. Vc is equal to 1 over C integral of IC dt, right? So C is equal to the integral of IC dt over Vc. What is the integration of current with time? Charge, exactly. So this is charge, and this is voltage. So if I am able to calculate the charge and the voltage, I know the charge and the voltage across between two lines or between any 2 points in space, then I can calculate the capacitance between the 2 points. Charge is easy because as long as you have current, you know what charge is deposited on top of the conductor. So you can assume, for example, we will assume that the conductors will carry a charge Q. And in a three-phase system, QA plus QB plus QC will also equal to 0 because the currents are balanced, so the charges are balanced in space in a certain area as well, right? So charge is like current in the inductance before. So what is really what we need to calculate? What is the, what we'll be spending time on? Calculating the voltage between 2 points in space. And the voltage between any 2 points in space is due to what? The electric field strength, which has a unit of volts per meter. This is an electric field strength. This field has a field strength of a certain volts per meter. If you have two surfaces with opposite charge, or two surfaces that are charged differently, ground, for example, and a conductor, right? Or two conductors, right? These are two surfaces that are charged differently, right? So two surfaces that are charged will have an electric field between them. This electric field has a strength of volts per meter. This electric field will be emanating out of the conductor, right? Electric field is perpendicular to the surface of the charge, where the charge is located, right? So this electric field will have a certain strength E. Of course, there's a medium which is this air dielectric has a certain permittivity, right? So that's epsilon naught. So, and if we're able to calculate or know what E is, this is the electric field strength between these 2 points. Then between in this area. If I want to take any 2 points in this area, 1 and 2, and look at the voltage difference between them, I will do what? Take small areas here, because the strength here is volts per meter. If I multiply by meter, right? If I multiply by that distance, and multiplication by the distance, or adding up these small distances, or all this distance together, is basically an integration of this electric field strength, right? So if I do this, then I will get the voltage between 2 points. So if I integrate the electric field strength between these 2 points, then I should be able to calculate the voltage difference. If I calculate the voltage difference between 2 points, I can bring 1 point on my conductor, same, and 1 point on another conductor, or 1 point on my conductor and ground, for example, right? And that way I will be able to calculate the capacitance between two conductors, or the capacitance between conductor and ground. If I calculate the capacitance between two conductors, this is due to the voltage between the two conductors, V1, 2, right? What is the voltage between, this is the voltage between two conductors. How about, what's the relationship between the voltage between two conductors and the voltage between one conductor and ground?
If it's between ground, isn't it just minus 0?
So this is the voltage between two conductors will correspond to a certain capacitance, right? How about if I have, now I would like to find the capacitance between, this is CAB. How about if I am, let's say a transformer terminals. These are two transformer terminals. This has a certain potential or charge. This has a certain potential. The voltage difference between those I can define as V12, for example. This V12 will correspond to a certain capacitance between these 2 points in space, right? How about if this transformer is centered out, connected to ground? then what is the voltage between this point and this point? If it's center, at the center exactly. That's what's the relation between V12 and Vx? Yeah, Vx is equal to half of V12, right? So if the voltage, if the voltage here is V12, the voltage here is half of that voltage here. So then I can calculate now the capacitance. If I calculated the capacitance between two lines, I can calculate the capacitance between one line and ground this way by looking at half the voltage. Half the voltage will give me twice the capacitance, right? This is, yeah, it was V12. V12 is equal to X, for example. Now this X is X over 2. Bring this 2 up here. So basically I will end up with double the capacitance. So if I calculate the capacitance between two conductors, take that multiply by 2, it's the capacitance between conductor and ground. And that is my interest. Remember, my equivalent circuit is this. This is my short line equivalent circuit for the transmission line. I'm trying to calculate the capacitance between the tower and ground. So I will first calculate the capacitance between 2 points in space 1, 2, or two conductors, and then basically multiply that by 2 to calculate the capacitance between tower and ground. Then divide it by 2 again, because this is JB over 2. This is, they put half the susceptance here, half the susceptance here, right? So that's where this is all going. So do you see the relationship between, chapter 4 and this now? We filled this now, and we filled this now. We just need to fill this, but we don't have time to fill it today. So next class we'll wrap up this capacitance.
So this is still chapter 4, right?
Yeah, this is chapter 4, but really you have to pay attention to what I'm saying in class, because chapter 4 has a lot more stuff. I'm simplifying it significantly. Like, we will finish chapter 4 next time and start the next chapter. So, but I skipped a lot of stuff. They give more details. For example, I don't get into bundled conductors. I don't get into strands and how the effect of the strands on the radius. I don't get into a lot of details, because I want to give you an idea. Okay, this is how we do it generally. Fine. Everything else will be a little bit okay. Fine tune what I said on a stranded conductor. Everything we're doing was more a solid conductor. I was considering the radius. Okay, if it's not a solid conductor and it's stranded, it's not radius anymore, you have to use a geometric mean radius. How about if it's not a stranded conductor, it's a bundled conductor? So this phase is made of 4 bundles. The radius will change, but at the end of the day, and there's a way to calculate the corresponding radius, but there will be a radius that you would use in the same equation that I have, right? So I won't spend, I can spend another class and a half on this, but I prefer to spend another half class, then start another topic again, okay? Because really it's just more detail, and that detail you can read. I don't think you need to spend too much time on it. We'll stop here.